Hello, my name is Jaehee Jang. I'm a PhD candidate at Seoul National University. The paper I'll be presenting today is titled FedClassAvg, Local Representation Learning for Personalized Federated Learning on Heterogeneous Neural Networks. This is a joint work with Heoneok, Dahuin, and my advisor, Professor Yoon from Seoul National University. This work was also funded by LG Chem and LG Innotek. The outline of this talk is as described in the slide, and I will explain the motivation for the study. As deep learning has made remarkable advances, it is now being used for a wide range of applications. And because deep learning requires a large amount of data to perform well, even private and personal data shown in the figure below have to be collected at one place. However, this kind of work can pose a serious privacy threat to the data holders. That's why one of the reasons why federated learning, or FL, was proposed, to train multiple data sources without collecting or sharing themselves. Yet, since each client collects data by their own, this data distribution of clients is non-identical and independent, or non-IID. So the training result of conventional FL performs generally well, but could do poorly on local data distributions. Thus, personalized federated learning, or PFL, was proposed. It consists of a collection of federated learning algorithms that allows solid performance on their local data distributions as well. However, most PFL algorithms assume all clients to use the same model architectures, which becomes another personalization constraint. Thus, the need for PFL algorithms for heterogeneous models, where clients use different model structures, has emerged. The main challenge was how to allow multiple clients with different data distributions and model structures to learn together. Most of the existing PFL algorithms on heterogeneous models are based on knowledge distillation. These algorithms provide public data to clients and collect their responses instead of model weights. This enables communicating and sharing of locally learned knowledge between different model architectures so that clients are free to select local model architectures. The downside of this technique is that expensive or sometimes infeasible auxiliary data collection must be accompanied. Furthermore, the server might request clients to provide metadata or of their models, which could be a hint to data privacy. Also, the distillation step is done on the global server, which requires extra computation and storage on the server. To address this, we propose federated classifier averaging, or FedClassAvg, which is a novel PFL framework for heterogeneous models. The main idea of FedClassAvg is based on most of the neural network models for supervised learning are composed of a feature extractor and followed by a classifier. The feature extractor determines the location of the input data on the feature space with the feature representation vector. Then the classifier determines the decision boundary between the mapped features. Therefore, FedClassAvg unifies and aggregates classifiers to share the trained knowledge. The purpose of PFL is to make the client perform better when training alone. We believe that the feature extraction capabilities can be sufficiently learned through the local data distribution. And unified classifiers will unify the decision boundaries of classifier models, which will become collaborative knowledge. Moreover, this also enables clients to select different architectures with minimal adjustment. Because in general, we identify the architecture of a neural network by the feature extractors, not by the classifiers. If the decision boundary in the feature space is unified through the classifier, Clients can share the knowledge of where the representation should be located and classified. So different client models can train collaboratively. FedClassAvg achieves this by a two-step training method, global classifier update and local client update. At the global classifier update state, the client classifier weights are aggregated and averaged to become global classifier weights. The process is as follows. First, clients transmit local classifier weights to the server. Then, the transmitted local classifier weights are combined as a global classifier by averaging. Finally, the global classifier is broadcast to clients. At the client update step, there are three training objectives. First, supervised contrastive loss, cross-entropy loss, and proximal regularization. Supervised contrastive loss controls the distance between feature representations. Specifically, the representations of the same class to be close and of the different classes to be far. Through this, the classification result is less affected even if the decision boundary determined through classifier averaging becomes slightly inaccurate. Cross-entropy loss is used for the supervised label training. And proximal regularization is the L2 distance between the local and global classifiers. This ensures that the local classifier is not too far from the global classifier while learning the previous two objectives. So, local client update proceeds as the following process. First, there are input data X and label Y, and we transform X into different augmentations X prime and X2 primes. Each feature representation, fx prime and fx2 prime, comes out through the local feature structure. Then we first compute the supervised contrastive loss for both representations and label Y. After classifier is done, classification is done on the first representation fx prime, cross-entropy loss is calculated between the predicted label Y hat and the actual label Y. In addition, the proximal loss between the local and global classifier is calculated. So far, we have looked at the proposed method. From now on, I'll talk about the empirical performance evaluation results of the FedClassAvg algorithm. The experimental setup is as described in the slide. We use cipher10, fashionMNIST, and EMNIST letters as evaluation datasets. We assumed both data and model heterogeneity. For data heterogeneity, we assumed two cases of non-IID label distributions. The first case is Dirichlet distribution sampling, and the second case is two-class sampling. The label distributions of cipher10, for example, is described on the figures on the right side. And for the model heterogeneity, we used 4 types of models. Each model consists of a feature extractor and a classifier. For the feature extractors, we used ResNet, ShuffleNet, GoogleNet, and AlexNet backbones, followed by a fully connected layer. This fully connected layer projects the extractive representations from the backbones to have the same dimensions of 512. In experiments, we used 20 clients in total, and the model structures were equally distributed. In other words, there were 5 clients of the same model architectures. Then, for the classifier, we used a single fully connected layer, which shares the same structure for all clients. And here is the experimental result when we performed heterogeneous model training on 20 clients. The table above illustrates the average test accuracy of clients, and the graphs below show the learning curves for each dataset and heterogeneity case. Here, baseline is when all the clients were only trained locally. The compared KDPFL is the latest PFL algorithm on heterogeneous models, which achieve the state-of-the-art performances. As it can be from all the experimental results here, Fed class averaging outperformed the existing methods. In addition, we also measure the performance when clients use the same model structure. In the table above, plus weight indicates when KDPFL or Fed class averaging share the whole model weights. It is for a fair comparison with Fed averaging or Fed prox in terms of the amount of exchange information. Even only with classifier averaging, Fed class averaging showed comparable or even better performance than Fed averaging or Fed prox. After exchanging the whole model weights, including feature structures, Fed class averaging showed significantly better performance than any others. In short, we confirm that Fed class averaging achieves the state-of-the-art performance. To demonstrate that the proposed method allows collaborative training between different models, we visualize the feature representations from each client model using t-SNE plots. The feature representations were calculated from 20 clients trained with heterogeneous training settings. The same color on the plots indicates the representations of the same class. There seem to be some clusters within the same class representations because of local distribution discrepancies between clients. Still, representation of the same class are gathered after Fed class averaging training. Furthermore, we confirm that the layer attributions at the classifier layer. We did this because the fully connected layers can be easily affected by the positional information of the input. In other words, if the order of input elements is changed, it does not function properly. So we believe that if collaborative training is done between clients, we expected that when classifying images for the same class, even different clients should refer to similar locations. To confirm this, we measure the layer conductance at the classifier layer. As a result, we confirmed that the attributions appeared almost similar between different clients. Therefore, it can be said that Fed class averaging sufficiently enables collaborative knowledge exchange between clients. For the ablation study, we assess how the three elements of Fed class averaging affect the training performance: classifier averaging, proximal regularization, and contrastive loss. Both proximal regularization and contrastive loss contributed to the performance improvement. Among them, contrastive loss had the greatest impact. Still, Fed class averaging performed best when all the three components were combined. Finally, we compared communication costs between conventional FL, knowledge distillation-based PFL, and the proposed method. We measured communication cost of the conventional FL by the size of model weights, since they share the whole model weight parameters. For KDPFL, we measured the size of public data and their sub-predictions. Finally, as described in the table below, the expected communication cost is the lowest at Fed class averaging because it only shares a single fully connected layer weights. In conclusion, we propose Fed class averaging to achieve a high-performance PFL algorithm with heterogeneous model in this study. Fed class averaging utilizes classifier averaging, local representation learning, and proximal regularization to enable collaborative training between different model architectures. We also demonstrated that the proposed method outperforms the existing studies in terms of both training performance and communication costs. These are the references of papers and images used in the slides. And this is all from all for my talk. Thank you so much for listening.